Yeah, hi, good evening. You're welcome, guys. Welcome to tonight's class. You're really welcome. Thank you for joining. Yeah, you're welcome, guys. Welcome to tonight's class. Uh, it's been a very great moment in these classes, and tonight we'll be delving into uh, much more on probability. We have quite some things to cover, and just like you guys have been doing, I would love you to continue while I drop a question. I would love to get your responses as soon as possible. All right. So, in tonight's class, we want to get a little bit into intersection of events. We want to also talk about independent events. I want to talk about mutually exclusive events, and we also want to talk about, if possible, conditional probability. All right. All right. So, yesterday I gave you an assignment. Do we have the answer to the assignment yet? Three over five. Okay. 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 All right. Okay. So, let's try and see if we can quickly do that so that whoever did not get that answer, you have you're counting from 1 to 100, and the first event was, so counting from 1 to 100, you have the first event as multiple of 2. Am I right about that? And the second event, event B, was multiple of 5. Now the question was for you to find a probability that a number is divisible by 2, 5. Now, first of all, I want to use this as a good revision for what we did yesterday. All right. Uh, you see, when you are asked to find probability a number is divisible by 2 or by 5, when you're counting from 1 to 100, first of all, you have to, as usual, you have to go out to bring out the event space of event A, the multiple of 2. Now, because of time, I may not want to bring out everything, but you guys can understand multiples of 2 will be 2, 4, 6, 8, on and on, up till what? 100, because 100 will also be a multiple of 2. For event B, multiple of 5, we have 5, 10, 15, 20, up until we also have 100. Now you're told to find the probability that a number is divisible by 2 or 5. That means probability of at least one of them divisible by 2 or 5. Now, in this case, let's try and find out what is the number of elements in the event space of event A. So if you go on and do this math, you can see from 2 to 100, you're going to have 50 different elements. And if you do this math, what are you going to get for event B? What's going to be your number of elements for event B? What's going to be the number of elements for event B, guys? Of course, 20. Thank you very much, Omojola. Now, you also need to understand that probability a number is divisible by 2 or 5. That's obviously probability of A union B is divisible by 2 or 5. Now, you know what? Let me even be silent on the word probability first. Can you go on to count the number of elements? That means the number of elements that is divisible by 2 or 5. That means N A union B before you talk about the probability. Now, the point here is that you understand the reason why when we were trying to find N A union B, we said it was N A plus N B minus N A intersection B. The reason is because if you see a case like this now, N A is going to be all the elements inside here, the 50 of them. Now, the number in B, the 20 here. But there's something you are missing out on, is that there are going to be elements in A that are in B. And that was why you had to subtract them out. So the question is, what's going to be the elements that are in A and B? What's going to be these two? What's going to be A intersection B? What's going to be the event space for A intersection B? If you go on to find out, you cannot see 5 in both. You can see 10. You go on and on, you can see 20. If you go on and on, you will see you can see up until 100. Now, one thing you can notice is that this event is actually the multiple of 2 times 5. That's 10. So the multiples of 10 is what will be the event space of the intersection. So obviously, the number of elements in this multiple of 10, the number of elements in this multiple of 10 is actually 10. All right. You could go on to check this out. 10, 20, up till 100, you will have 100 different elements right there. Now, this means already that you try to find the probability of A in union B. The number of elements for A union B is going to be equals to, of course, NA is 50. NB is number of elements in B is 20. Number of elements in the intersection is 10. You go on to do this, you're going to get the total of 60. Now, I had to do this because I don't want you guys to get confused with finding probabilities. Because remember when I taught you in the first, I told you that the very most important thing is for you to, number one, understand the event space, whatever you're trying to find. And then you go on now to find the probability, which is always the number of elements in the event space over number of elements in the sample space. Now, if I want to now go on to find the probability of A union B, I can now go on to say it is NA union B over NS. NA union B is what? 60. NS, that means the total event space, sorry, the total sample space. You are counting from 1 to 100. That means the total sample space, the number of elements in the sample space will be 100. That was 6 over 10, which is what? 3 over 5. So this is exactly how you solve probabilities. All right. Now, let me see how you fare with this one, guys. We'll be going into intersection very soon, and that is going to lead us into, we're going to get into independent event. Very, very important for you to pay attention. So we have the probability of A being equals to 0.5. We have the probability of A union B being equals to 0.8. We have the probability of B as the question we are asked to find, given that probability of A intersection B is equals to 0.2. Can you get this in 5 seconds? Probability of A is 0.5. Probability of A union B is 0.8. Probability of B is the question, given that probability of A intersection B is 0.2. Can you give me that answer in just 5 seconds? So you're asked to find the probability of B here. Of course, you have to be versatile with the formula if you're going to be able to solve this. Now, you're going to have to make use of the formula of probability of A union B plus probability of B minus probability of A intersection B. Of course, probability of A union B was given as 0.8. Probability of A was given as 0.5. Probability of B is the subject of interest. Then you were given probability of A intersection B as 0.2. If you go on to solve this, obviously the probability of B, which was X, will be equals to 0.8 minus 0.5 plus 0.2. This will obviously give you a total of 0.5. All right, great. So let me see how you're going to solve this. Look at this. You have to be very careful of the language. I told you guys already, and you guys already said the probability has a lot to do with being able to interpret the question. So you have the probability of A being equals to 0.4. This is another question. Probability of B is given as 0.5. Probability of A union B is given as 0.7. You are asked to find the probability of neither A nor B. Neither A nor B. All right? You are asked to find the probability of neither A nor B. Can you do that very quickly? It's a very quick one. Can you give me the answer in like 5 seconds? All you have to know here is the language. Once you agree with the language, you cannot go wrong. All right? Do we have an answer? Okay, somebody says 0.7. Okay. The person retracted the answer. Somebody says 0.2. Okay. Hopefully that person doesn't retract the answer also. Somebody says 0.5, somebody says 0.2, somebody says 0.3, somebody says 0.2. Okay, let's see it. Now look at the question. Probability of A is 0.4, probability of B is 0.5, probability of A union B is 0.7. We have to find probability of neither A nor B. Another word of this is neither. None of them. None. Because don't forget, from yesterday's class, I'm sure you people remember what's another name I can use for this? If I was going to write this in word problem, this probability of A union B, what am I going to write? Can anybody remind me? What am I going to write if I'm going to write probability of A union B using word problem? What's something I can say instead of writing probability of A union B? Can somebody tell me what can I say? Or, well, not too bad. At least one. That's the question. That's anime vibe is correct. At least one is what I want to hear. At least one. I told you guys yesterday that probability of A union B is it's a way of saying at least one, because probability of A union B is probability of A or B or both, right? So probability of at least one is a way of saying it. Good. So the opposite of that, the complement of that is none of them, because at least one and none, they are complementary events. So at least one. The complement of that will be none. All right, that's the complement. This is, if this is an event, this will be the complement, none of them. So obviously, all you have to do here is very simple. Just do 1 minus 0.7, and that is 0.3. All right. So it's that simple. So this will be the last question on the union of events. All right. The last question I want to give now, pay attention to it. In a class of 100, in a class of 100, 60 take maths. So there's a class of 100, 60 take maths, 60 take maths, 50 take English, 40 take economics, 30 take math and English, 20 take math and economics, 15 take English and economics, 5 take all three. So the question is for you to find the number taking at least one subject. All right? You have to find the number of people taking at least one subject. The number taking at least one subject. At least one subject. So that's the question. Find a number taking at least one subject. Do we have an answer? Somebody said 80 students. Another person said 80 students. Okay. So we're told that the class was a total of 100, and 60 takes maths, 50 take English, 40 take economics, 30 take math and English, 20 take math and economics, 15 take English and economics, 5 take all three. All right. So find the number taking at least one subject. Find the number taking at least one subject. Some people said we have answers that said 80 students being correct. We'll solve very soon. Can we get other responses? Okay. Somebody else said 80 students. All right, guys. The number taking at least one subject, from what I explained to you in yesterday's class, Enoch said 90. Somebody else said 80. Let's solve together. Now, when you see questions like this is obviously a three-set problem. Under probability, I taught you yesterday, and I still reminded you today, that when you see at least one, we are dealing with the union. So in this case, we are dealing with the question. We are only interested in number here. So the number of A union B union C is what you are told to find. That's what you are trying to find. At least one. At least one. At least one. I told you already that A union B union C represents at least one. If you're dealing with a two case scenario, you'll be dealing with A as at least one. Now you're dealing with three subjects. It's A union, B union, C being at least one. Now, looking at this, I taught you yesterday that when you have the union of three events, it's very simple. It will be NA plus NB plus NC minus NA intersection B minus NA intersection C minus NB intersection C. And I went on to tell you that plus NA intersection B intersection C. So if you make an attempt to solve this, obviously NA, this is it. Now obviously will be 60 as NA. NB will be 50. NC will be 40, number of elements taking economics. NA intersection B, that will be math and English. The intersection of that will be minus 30. NA intersection C, that will be math and economics. That will be minus 20. NB intersection C, that will be economics and English. That will be 15. And then you have plus 5. All right. So we see what's going on here. You go on to solve this. This obviously will give you 150. This is minus 50 minus 5 plus 5. You solve this, it give you a total of 90. All right. Now, I want you to use this question, this same question, to find the number taking none. Guys, find the number taking none. Find the number taking none. The question is for you to find the number taking none. So question number B, find the number taking none. Somebody said 10. Somebody said 100 minus 90. Somebody said 10. Okay. The number taking none, of course, I do not expect that to be difficult at all, because you understand that I told you already, this is mathematical. At least one and none, they are complementary events. So if you have gotten for at least one, just understand that I told you yesterday, I said an element, an event rather, plus its complement must give you the sample space. So you can see that if 90 was at least one, the whole sample space was 100. Of course, the complement, which will be none, must be 100 minus 90. So the answer to that will be 100 minus 90, which will be 10. All right? That is how you solve questions on complementary events. You can see how we are using complementary events while solving union of events. So you have to understand all this detail, and you would never go wrong. So guys, let me get your feedback. How do you feel now about probability? We have done combination of events. We have dealt with union of events majorly, and it was really needful for us to solve several questions so that you people can get more versatile with solving questions. So how do you feel about everything we've been doing? Is it understandable? Right? Are you confident in your success for questions that comes out under probability? Okay, I like the feedback. It's going great. That's good. So let's delve quickly into intersection of events. And some of you may be surprised why we are going to still be talking about intersection of events. But from intersection of events, we are going to quickly jump into independent events. Now, intersection of events is obviously when we said A intersection B. So you are no longer new to this, all right? So I believe we have even solved questions around this. But I need you to understand that the intersection of events is something that, of course, you've been hearing it both. When you hear the word both, right? That's majorly the intersection. Now, there are certain type of events of which you may have a different way of solving the intersection. Of course, with what we have just said, if you have any question regarding intersection of events that has to do with the kind of questions we have been solving, you can easily just subtract. Of course, when you have A union B, the probability of this being equals to probability of A plus probability of B minus probability of A intersection B. Of course, if you are given this, and you're given this, and you're given this, you can obviously get your intersection through this formula, all right? But I need you to I want to open your eyes to other possibilities. For instance, there is a general formula that you would see in this form, that probability of A intersection B is equals to probability of A given B multiplied by probability of B. Or it's possible, depending on the context, for you to have probability of A intersection B being equals to probability of B given A multiplied by probability of A. This is what we call Bayes theorem under probability. But I'm going to come into this while dealing with conditional probability. But you just need to pay attention. I'm going to explain. It's quite very, very simple. All right? It's quite very simple, and I would love you to really pay attention. Don't look at this as anything. A given B is very simple. B given A is very simple. I'll explain this in a moment. And I'm also going to talk about independent events. All right? Now, look at this first one I wrote right here. We have probability of A intersection B. And I said this or this. Let me just give you a feel of this so that you don't get too confused. Look at something, guys. Generally, you only see this when we branch into conditional probability, possibly this night, if not possible this night, probably some other time. Probability of A intersection B is coming from this general formula. Look at this. Look at this right here. Look at this right here. Probability of A given B. You're going to see questions like this. I believe this night you're going to solve a question like this. They will tell you probability of algebra. Like for instance, if the probability of algebra given the student did biology, something like that, you know, you will see questions that has to do with probability of something given something. You know, when you hear the word conditional probability, there's a condition attached. Probability of something given that this has happened, probability that this happened given that this has happened. That's where all this is coming from. Probability of A given B. It's more like saying probability that A would happen given that B had happened. Something like that. So that's the whole context around what you're seeing right here. Now, under Bayes' theorem in probability, we said the probability of A given B is equals to probability of A intersection B over, now look at this right here, probability of what? B. The question is, how do we know if it's probability of B here or probability of A? Whatever was the given, so this means if I was going to find probability of B given A, of course, that would be equals to probability of A intersection B over probability of A. You can see what's going on here. It's a case of understanding how the whole context of the question is going. So if it's probability of something given something, what you need to understand is that it's going to be probability of the intersection over the probability of whatever was given. That's just the way it moves. So if it's probability of B given A, it's going to be like this. That's the reason why you see when I wanted to define probability of A intersection B, I said, of course, you guys understand cross multiplication very well. If I have to cross multiply these two things, you know that probability of A intersection B will be this times this. That's this one. But in the case where I'm dealing with probably B given A, then of course the intersection will be probability of B given A multiplied by probability of A. That's where all this is coming from. So these are the general way, depending if you are solving a question that has to do with conditional probability, this is how you tackle those kind of questions. So you have to know, of course, you already know this very well. All right. Can you guys still hear me? Hello, you guys are welcome. You're welcome back. That was a glitch. I do not know what's up. I probably a network thing or something. So sorry for that. Yeah, so yeah, so as I was saying, yeah, so we have uh I'm trying to expose to you several ways of solving questions. Please, am I still audible to you? Can you please confirm if I'm still audible? Okay, it's all right. Okay, so I was trying to expose to you several ways. You have to be very versatile when doing probability because some questions can come and you have enough data to use this first formula. All right. Very possible that you were given the union of the two events and probability of this event, and then you can easily find the probability of the intersection using this first formula. Now, you could have another different scenario where you are given a case where you are having a conditional probability where you are told that the probability of something given case now you don't even have enough data to make use of this first. Does it make sense? So you cannot use this first formula to solve in a case where you're given a case like this. So you have to understand this one also. And I explained to you how this formula was gotten. It's just gotten from this general formula, which we call Bayes theorem. Probability of A given B is equals to probability of A intersection B over probability of B. And the way to bring this formula out is whatever was the given something. In this case, given B was the case. So that was how we got the denominator here. In this case, given A was the case, and we got the denominator as A. That's the whole thing around it. All right. Now, pay attention to something now. Another different scenario can be if you're told that these two events are independent. That's a totally different ball game again. So if you're told that the two events are independent, the way to find the intersection is this. So I was trying to say before the network went out, in anything you do, please never forget this formula. You understand that from my own experience, I can easily tell you some things that are very common and very easy to manipulate students. This formula is very key because many people wrap their head around this one. All right. They forget that when they tell you that two events are independent, the probability of their intersection is probability of A times probability of B. Note this so well that you never forget, guys. Please, I know exactly what I'm saying. Make sure this is at the back of your hand. All right. Now, probability of A intersection B, given that the two events are independent, is given as probability of A multiplied by probability of B. That's very key. So we're going to be going into solving lots of questions now. And as we always do, I would love you to shoot your answers right here in the chat box. All right. So you're going to be seeing, I'm sure you have written all the formulas down. The very first question will be obviously on independent events. So let me just see your knowledge if you have gotten what I said. Guys, look at this very interesting question. The probability of A is given as 0.4. The probability of B is given as 0.5. Now, the probability of A intersection B is given as 0.2. Now, look at the question. The question said, are A and B independent? Now, guys, while you're solving that, let me give you a little understanding around independent events. You see, the meaning of independent event, as the word implies, independent, that means the probability of this doesn't depend on the probability of this. So, of course, they are dependent. They are going to be dependent if probability of one occurring depends on the probability of something occurring or has occurred already. So, independent event has everything to do with if the two events do not in any form or way depend on each other. Let me give you an example very quickly. Imagine we have two events. The first event was let's say you have a coin and a die in your hand. All right. Look at, you have a coin in your hand and you have a dice in your hand. You're going to shuffle these two things in your hand and you're going to throw them up. Now, guys, I want to ask you a question very quickly. The probability of you seeing a head on the coin, is it dependent on a 2 showing in a dice? That's a question for everyone. The probability of a head showing up on this coin, is it dependent on a 2 showing? Someone said yes, someone said no, someone said yes. Okay, that brings us to the real concept of independent event. You have a coin here, you have a dice here. I want you to understand that this coin has nothing to do with this dice. Head doesn't show up because a 2 show up. Head doesn't show up because a 6 show up. Head doesn't show up because a 5 show up. Same thing as for tail. Tail doesn't show up because you have a 3. If you throw the two objects up, whatever comes from the dice will be independent of whatever comes from the coin. The coin and the dice, they are independent. This is a very good example of independent event, because the fact that a head show up on the coin doesn't in any way relate with a 2 showing up. So a head showing up does not affect the possibility of a 2 showing up. It's like saying, are you going to say, because I held a coin, then I'm not going to ever get a 2 again? Are you guys, for those of you that were answering yes, that they are not, or saying they are not, like they depend on each other, are you saying if you held a die in your hand, are you telling me that if a head show up on the coin, you will now say, oh, because a head has shown up, I can never get a 2 on this die? Is that the way it works? Of course not. They are independent. It's the definition of independent event. One occurring doesn't prevent the other one occurring. Now, the intersection of these two events, that was what I just showed you. Intersection. So probability of A, let's say event A was a head showing up. Let's say event B was a 2 showing up. Probability of A intersection B with probability of A multiplied by probability of B. This is the concept for independent events. Now, look at it. Look at this question you are given. Probability of A is 0.4. Probability of B is 0.5. Probability of A intersection B is 0.2. You will now ask that A and B are the independent events. Of course, what do you have to do? What's A and B? A intersection B, 0.2. Go and check. You want to check if they're independent. This must hold. If they're independent, this thing must hold. All right. If this doesn't hold, then it's not independent. If probability of A multiplied by probability of B is not equals to probability of A intersection B, then it's not independent. Now you have been told probability of A intersection B is 0.2. So let's go and see if we are not sure if it's equal to, we want to find out if it was equals to probability of A times probability of B. What's probability of A? 0.4. What's probability of B? 0.5. Guys, what is 0.4 times 0.5? 0.4 times 0.5 is what? Zero point 0.2. So this is obviously 0.2. Can you guys see that probability of A, probability of B, which was 0.4 times 0.5, which was 0.2, is equals to the intersection. So therefore, we conclude that these two events are independent. All right? They are independent. Okay, so that's a good introduction. I believe you should get the best from that. All right, look at this question now. If events are independent, probability of A equals to 0.6. You can take it down quickly because of time. Events are independent. You are told now that the events in this case are independent. All right. Probability of A is 0.6. Probability of B is 0.3. You have to find probability of A intersection B. Don't forget, they told you events are independent. Are you seeing the way this works? Like, once you hear the word events are independent, you know exactly what to do. So what is probability of A intersection B? Somebody wrote 0.18. Another person wrote 0.18. It looks like everyone is agreeing the answer being 0.18. Of course, that has to be the answer because we know that if two events are independent, probability of A intersection B is equal to probability of A multiplied by probability of B. In this case, probability of A is 0.6, probability of B is 0.3. This will give you 0.18. All right? You understand the reason why I said you should always note this formula. Now look at this question. Probability of A is equal to 0.5. Probability of A intersection B is equal to 0.2. What is probability of B? That's the question. What is probability of B? Somebody said 0.4, somebody says 0.4, somebody says 0.4. People are saying 0.4. Let's find out. Of course, probability of A intersection B when they are independent is equal to probability of A multiplied by probability of B. You can see the reason why I'm repeating the formula so that you people can be grounded in the understanding. So it's good practice. That's a very good way to understand formula. So you do not know probability of B. Of course, you have to find probability of B now as 0.2 divided by 0.5. That will give you a total of 0.4. All right, good. All right, two fair coin are tossed. 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 Now, let me quickly pause there and explain it to you quickly. When you see the word fair being said in questions on our probability, this just means that fair means they are not biased, meaning that there is nothing on the coin that will make it to tilt towards head or make it to tilt towards tail. So that's the essence of writing the word fair, meaning that they are not biased towards any outcome. All right. Two fair coin are tossed. A represents that the first coin is head, first coin is head, and B represented the event that the second coin is head also. So the question now is for you to find P A intersection B. Guys, this is not too technical, but it's a bit higher than all the ones you have been solving. Two fair coin are tossed. Event A represented that the first coin is head. Event B represented that the second coin is also head. You are told to find the probability of A intersection B. Okay, someone wrote 0.25. Some other people are seconding that 0.25. Now, guys, pay attention. Some of you may probably be trying to understand what is going on here. These things are very simple. Notice in this question, nobody told you if they are independent or not. The reason for that is because they expected you to understand that when you toss two fair coin up, you need to understand that that's a very great example of an independent event, because obviously the two coins don't in any way depend on each other. The outcome of the first coin has nothing to do with the outcome of the second coin. So you can't say they are dependent. No one is depending on anyone. So this is a perfect example of an independent event. So looking at this, the outcome of event A was that the first coin is head. The question is, what's the probability of A, first coin being head? What's the probability of you getting the first coin as head? Now, if you have been following the classes, I'm sure you understand that when you have the first coin, or a coin being thrown up, the probability of getting head is actually 1/2, of course, because in a coin you have, I'm sure you remember that probability is always NE over NS. For that first coin, the event now is to have head, which you only have one head there, right? And the total number of possible outcomes is 2, because you have head or tail. That's how we got 1/2 there. The same thing goes for probability of B, the second coin. The probability of getting head in the second coin is also 1/2. So you have to calculate these two things on your own. Then you now need to go on now to apply this with your general formula that you know that when two things are independent, the probability of A intersection B is probability of A multiplied by probability of B. Are you understanding the importance of noting all these things now? If you do not know this formula, or you do not know how to define independent event, it will be very hard for you to come up with these answers. So guys, I'm really hopeful that everyone is paying attention and you're understanding what's going on here, because these are very examinable aspects of probability. So the answer is actually 1/4. All right. All right. A next question now, very quickly. A die is rolled. A die is rolled. A die is rolled. So you are rolling a die in this question, and look at it right here. A die is rolled twice. Sorry, you are rolling the dice twice. Event A was that the first roll is 6. All right. Event B is that the second roll is even. All right. The question is for you to find the probability of event A intersection event B. I really hope you guys are really following, because if you don't have proper understanding of this subject, it will be confusing in an exam. But if you really understand independent events and every other aspect of events, union of event, intersection of event, you can never go wrong. You cannot miss any question on probability. I'm very certain of that. So look at this question right here. Do we have anybody answering the question already? A die is rolled twice. Nothing is being told about if they are independent or not. You have to be able to look through this and know if this is independent or not. Somebody said 1/9. Somebody said 0.12. Somebody said 1/12. Somebody said 1/9. All right, we have varying answers. So let's try and do it together. A die is rolled twice, right? A die is rolled twice. Now, if this die is rolled twice, guys, first roll is 6. Second roll is even. I want to ask you a question quickly. Is this an independent event or not? That means, does A depend on B or does B depend on A? Are they independent or dependent event? Do these have any dependency on each other in any form or in any way? Can anybody give me an answer there? Because don't forget, imagine you're in an exam hall, nobody would actually tell you that a die is rolled twice. You were told that A is the first row getting 6. Somebody said it's a dependent event, somebody said it's an independent event. Can you buttress your point why you said it's a dependent event? Can you buttress the point why you said it's an independent event? Now, the first row being 6, the second row was even, right? So why would you say this is independent? Why would you say this is dependent? That's very vital. Once you have the right understanding, you don't miss questions like this anywhere. So if you look carefully at these two things, when you have a die, you throw it up, you get something. The question said the first roll was 6. You threw that die up again, and the roll gave you an even number. Guys, the first rolling and the second rolling, they don't depend on each other. All right? They don't depend in any form or way on each other. So even though they did not tell you this was an independent event, you should know already that this is an independent event. So before you go on to try and find the intersection, first ask yourself, is this an independent event? Because if it's an independent event, the way to find intersection is different. Of course, it's a different thing. So you should not go on trying to find any other thing apart from that for independent event. So obviously, you know that the probability of A intersection of B under independent is probability of A multiplied by probability of B. All right. Now, looking at this, the question is, nobody told you what probability of A was, and nobody told you what probability of B was. You have to go on to find it yourself. So guys, how do we find probability of A? Probability of A was that the roll was 6. So what's probability that with that first rolling was 6? Probability of getting a 6 when you throw a die up is what? Is 1 over 6. I believe everybody is very versatile with this already. I don't believe anybody is here being confused on how we got 1 over 6. All right. Now, what's the probability of you getting the second event happening? Second roll is even. All right. Now you have the outcome, the possible outcome on a die as 1, 2, 3, 4, 5, 6. So the question is, what's the event space for having an even result? Of course, the event space will be 2, 4, and 6. All right. So therefore, the n number of elements in the event space here is 3. And I told you probability is always going to be NE over NS. What's NS? NS is 6. So probability of this event, of course, even happening is going to be 3 over 6. That's going to be 1 over 2. All right. So the probability of B is 1 over 2. So following what we just have to go on to say 1 over 6 multiplied by over 2. That will give me a final answer of 1 over 12. All right. That's how nicely you can get every question being given to you on probability. It's quite very easy once you understand the concept. All right. Now let's see another question. Very important you solve as many questions as possible to get your feet grounded under each of all these concepts. All right. Now you're told that the probability of A is 0.7. You're also told that the probability of B is 0.4. And you were told that the probability of A intersection B is 0.25. Guys, the question is, are they independent? The question is, are they independent? All right. That's the question. Are they independent? What's your answer? Okay. We have some people. Okay. People are saying they are not independent. All right. Now it looks like we can make a try on that and see if you people are correct. Of course, you are asked if they are independent or not. The check for that is just go on to check if this formula is correct. That means if probability of A intersection B is equal to probability of A multiplied by probability of B. So go on to have probability of A multiplied by probability of B. That will be obviously 0.7 multiplied by 0.4. That will give you 0.28. All right. And you were told that probability of A intersection B was 0.25. So obviously this is nice and simple. You can see that probability of A intersection B is not equals to probability of A multiplied by probability of B. Therefore, they are not independent. All right. That's simple and straightforward. All right. Let's see another question quickly. Probability of A. I hope I'm not too fast for anyone watching. Hope as I'm communicating the right way to you. I'm trying to expose you to lots of questions so that you are very sound in probability. These are one of the questions you can never avoid them in any exam you are preparing for. I can assure you, you would see questions on probability. It's one of the most constant question in statistics. So that's the reason why you have to be very, very exposed. All right, look at this question right here. Probability of A is 0.5, probability of B is 0.6. Now to find probability of A union B. Guys, why do we have that number of thumbs up when we have an higher number of viewers? Why don't you give a thumb up to this video? All right. Somebody says 0.3, somebody says 0.3, somebody says 0. Okay. Somebody says 0.33, somebody says 0.8, somebody says 0.8, somebody says 0.7. All right. Somebody says 0.3. Okay. It's time for us to solve this. Since we have varying answer, it will be good for us to solve this very quickly. Now look at this question right here. One thing I needed to have added was for you to understand that their probability of A and B are independent. All right. So if A and B are independent, of course, the first thing you can find from independent event, the knowledge of independent event, is that probability of A intersection B will be probability of A multiplied by probability of B. And that will obviously be 0.5 multiplied by 0.6. That will be 0.3. Probably you people did not see the question that was asked. You were asked to find probability of A union B, not probability of A intersection B. All right. So many of you went on to find for A intersection B. All right. You were told to find A union B. Of course, that's a warning. So you have to pay real attention to the question so you don't look through on a question and you are solving something different. All right. Looking at what we have here, you need to remember that probability of A union B, which you know already, is probability of A plus probability of B minus probability of A intersection B. This is a very good way to, of course, this is very vital when you can also use this for independent event because this is the general knowledge on union of events. But the only difference is that your probability of A intersection B will be gotten from the knowledge of independent event. So you can see that for us to get probability of A intersection B, we had to revert back to our formula that we use while dealing with independent event. So in this case now, to get this probability of A union B, that will be 0.5. Added with 0.6, subtracted, you'll be subtracting 0.3. So this will obviously be 1.1 minus 0.3, and this will give you what? 0.8. All right. If they are dependent, obviously you'll be missing information here because if they are dependent events, someone is asking if what if they are not independent events. If they are dependent, then you would have needed an information separate from what you have here. So you would have to find a way, which in many cases you'll be given this. If you're not given a diagram, or just find a way to get this answer, of course, you will not be able to use the independent formula because that will not work in that case. So you should understand that if they are dependent, this is not the way to go. You cannot use the formula for independence. All right. Look at this question very quickly. If A and B are independent, prove complements are independent. If A and B are independent, prove that their complements are independent also. If A and B are independent, prove that the complements are independent. So you can go on to use anything you want to use, by the way, but anything you want to use, you can use any. In this case, when you're trying to prove something, you are at will to do whatever you want to do. You can use any figure, but just in case, when I'll be solving, I'll be using the figures you see right in front of us. So I'll be using probability of A being 0.4 and probability of B being 0.5. But obviously, you can go on to use anything you want to use. So of course, it's like you are asked to find that the complements are independent. So if you want to prove that the complement, of course, that means you are asked to find out that you want to know that A complement and B complement, they are also independent. In this case now, if these two things are independent, of course, you know that the probability of A intersection B in this case should be 0.2, right? But that's not what matters to us. What matters to us is that we want to prove that this is independent. So obviously, what you can just do is to go on to say the probability of A complement. Probability of A complement will be what? A complement, you know already, will be 1 minus probability of A. That will be 0.6. Okay, let me write it. 1 minus 0.4. That will be 0.6. All right. And B complement will be 1 minus 0.5. That will be 0.5. All right. Now, if you go on to probability of A complement multiplied by probability of B complement, that will be 0.6 multiplied by 0.5. That will be 0.3. So this is just this is obviously just this originally you have to find probability of A complement intersection probability of B complement. Now this was obviously this. So probability of A complement intersection B complement will be equal to probability of A complement times probability of B complement, since they are obviously independent. All right. So this is just this is more of proof. You may not focus too much on proving. All right. Look at this question. Two independent events. The first one was add probability of A. The first event was 0.3, and the second probability of B was 0.4. All right. This was the data you were given. So the question is for you to find a probability that at least one occurs. All right. Yeah, I'm not focusing more on the proof. All right. I'm focusing more on just answering this question, because the proof is not very. You can't move through this using the proof. It's just the same. It's not very. It's going to be independent, obviously, but we can't use what we are having here to prove it. And since proving is not one very essential part of the scope of what you're working on. So I don't want to spend more time doing that. In this case, we have the probability of A being 0.4, sorry, A being 0.3, probability of B being 0.4. You have to supply the probability that at least one occur. At least one occur. Now the question is for you to give me the answer for probability that at least one occur. So we have 0.58, 0.12, 0.68 as different answers given. All right. Probability of A is 0.3, probability of B is 0.4, and probability that at least one occur. This was basically used because for you to be very versatile with being able to interpret all these word problems. When you see probability of at least one occur, understand that they actually find probability of A, B. That's the point. So writing it that way so that you are at least open to this. So now look at this. Probability of A intersection B. Of course, you know that probability of A union B is probability of A plus probability of B minus probability of A intersection. Is you have probability of A here as 0.3, B here as 0.4. So the question is, what is probability of A intersection B? Since they are independent, then you know that probability of A intersection B will be probability of A multiplied by probability of B. So this obviously will be 0.3 plus 0.4 minus 0.12. This will give me a total of 0.58. So this is how you solve questions like a pro. You're getting better. I can see many of you are getting really better at probability. It's really great. That's great to see because that's the essence of all this we're doing. I'm sure you are preparing for your test. I'm sure you guys are going to eat it up for breakfast. So if I was going to ask you, what's the probability that neither, the first question said, what's the probability that at least one occur? What's the probability that neither A nor B occur? So this was the probability of at least one, right? At least one. So what's the probability of neither A nor B occur? What's the answer to that? What's the probability that neither A nor B occur? Yeah, obviously, what you just have to do, of course, you just go on to say 1 minus 0.58 because I told you already that neither, that's none of them occurring, and at least one, they are complementary events. So 1 minus 0.58 will give you 0.42. Another way of doing that, let's move through another different way, would have been for you to go on and find the complement. That means probability of A occurring, what's the probability of A complement? Then what's the probability of B complement? Probability of A complement would obviously be 1 minus 0.3 because you already understand complementary events. If probability of A is 0.3 and you are trying to find the probability of the A complement will obviously be 1 minus 0.3. So that will be 0.7. I'm sure everybody in this class understands that by now. If you are trying to find probability of B complement, that will be 1 minus 0.4. That will be 0.6. So for you to find probability that neither A nor B occur, all you have to do is you could move through this route and just say the probability of A complement intersection B complement, because that's probability of, look at it this way. This is probability of A complement is saying not A not occurring, and this intersection, I want you to understand it's mostly read and union is mostly read or. So when you say union, it's like saying or. When you say intersection, you are saying and. So it's like saying probability of A not happening and B not happening. All right, because A complement is the intersection. If A was the event happening, complement will mean not happening. If B was the intersection, sorry, if B was an event, B complement will be the, of course you understand that part of things already. So this is read as probability of A not happening and B not happening. So neither A nor B, obviously this is another way to write that. So this will obviously based on the fact that they are independent with probability of A complement times probability of B complement, since they are independent. Since they are independent. So that will obviously be 0.7 multiplied by 0.6. That will be 0.42. So you can move through any direction you want to move through, but this is good for being versatile, all right? Now, have this question also. Let me see what you're going to do with it. Now you have probability of A being equals to 0.5, probability of B being equals to 0.4, probability of C being equals to 0.2. Guys, what's the probability of A intersection B intersection C? Given that A, B, C are three independent events. Given that A, B, C are three independent events. So what's going to be the probability of A intersection B intersection C? Do we have an answer yet? Somebody says 0.04. Somebody says 0.04. Okay, it looks like we're having a unanimous answer around 0.04, and that should come with no surprise because to solve probability of A intersection B intersection C, you have to do is go on to just say, since they are independent, of course, it's going to be probability of A multiplied by probability of C, sorry, probability of B and multiplied by probability of C. So we're going to have, of course, 0.5 multiplied by 0.4 multiplied by 0.2. And if you do this, you're going to get a total of 0.04. All right, the next question is a bit technical. I'm going to see what you guys do with it. Technical, but very simple, but you have to really understand. You really have to understand the concept. You need to understand what I explained to you in probably the first class or the second class, one of the two. So you have probability of A being 0.6, and you have probability of B being 0.5. Now to find the probability that exactly one occurs. Find the probability that exactly once occurs. But find the probability that exactly one occurs. Somebody says 0.8. Okay. Okay. We have other answers. Somebody says 0.8 also. Someone says 0.06. Okay. Okay. More people are responding with 0.8. Okay. I said already that this is quite technical. Well, just so you know, nobody has gotten the answer yet. All right. Probably we solve together so that we can get right into it. Now, this is, remember, do anybody here recollect okay, it looks like Folashade has gotten the answer. All right. Do you guys recollect? I told you guys something. There's a reason why we do everything we do right here. I remember when we started the class, probably the second class, I remember drawing something for you people. It was your way out for a question like this. But I'm sure many of you felt not, it wasn't important. It was a tip for you to be able to crack questions like of this sort. Now, I told you I was trying to explain the union of events. How many of you recollect this when I was trying to explain it? Anybody here? You recollect when I was using the Venn diagram to explain union of events? Right? Now, I told you that for you to talk about the union of these events, the union will be shading everything, of course. I'm sure many of you know that, if not all of you. You shade everything. That's obviously the union of the event. Now, I was trying to explain to you how we get the formula for probability of A union B. And I told you that obviously it was probability of A plus probability of B. And I said minus probability of A intercept B. And I explained to you the reason why we have this way. And I went on to use this concept to explain that for a three set solution problem. And I explained to you that the reason why we have probability of A, I told you that what I'm circling around now, all this represents probability of A, all those things. Now, what I circle around right now again represents probability of B. And this right here in this middle represents the intersection, probability of A intersection B. Now, I explained to you that the reason why we're subtracting one of this probability of A intersection B is because while we wrapped this probability of A, we wrapped the intersection, one of the intersection with it, obviously. Now, when we wrap this, if we just went on to say probability of A plus probability of B, that would have been wrong because we would be having two probability of A intersection B included there. That means we would have had a situation where, of course, when I wrap this, I added that. When I wrap this, I had that. This was why we went on now to subtract one probability of A intersection B, so that only one is part of it now. So when we circled this, we held one, that was this. When we circled this, we had another one joining it, the same thing. So we removed one so that it can only be, of course, this, and this being represented. Now, when you have a question like this, look at now, back to the basis of why we are doing this. We're told to find probability that exactly one The meaning of exactly one now, if you're told to shade for exactly one, that's this. Because this black shaded portion is for both. You're not interested in both in this question. You're interested in just this side and this side. So the way to solve that, the way to solve this probability would be for you to obviously go on to not subtract 1 now. Don't forget, when we subtracted 1, we were trying to talk for A or B or both. That was what we said when dealing with union of events. We said this represented A or B or both. That was why we still add one of the intersection left. Now, if you're interested in having just A only, B only, what you have to do is simple. You will be subtracting 2 of the intersection because, of course, A plus B minus 2 of this will remove all of the intersection. So we'll be having exactly 1 occur. That will be probability of exactly 1 will obviously be probability of A plus probability of B. Of course, this probability of A plus probability of B, don't forget, they both included 1 intersection each. So when we wanted to deal with A or B or both, we left 1 intersection. We only subtracted 1 because both of them are holding each 1 intersection. But in this case, where we are just interested in 1, we will be subtracting 2 intersection. That will be 2 probability of A intersection B. So if you solve this formula, you will be getting for exactly 1. All right, because exactly 1 means A only or B only. Exactly 1, don't forget. Exactly 1 here, you need to also understand this side of things I'm saying. You cannot, exactly 1 is not just A. It's not A only. You cannot say exactly 1 means A only. No, it's A only or B only. So the only thing you are not interested in here is the intersection. So what you're looking for here is the union of A only and B only. So, and that's why you're going to put that together. So this will obviously be, of course, 0.6 plus 0.5. But the question now is, we don't even know what our intersection is. Now, this is where our understanding of independent event comes in. Of course, this will be 2 because we know these 2 events are independent. And what you have to do is to multiply probability of A multiplied by probability of B. It will be 0.6 plus 0.5. Of course, 0.6 times 0.5 will give you 0.3. That will be 2 times 0.3. When you solve all this, you'll be getting 1.1 minus 0.6. And you get the total answer of 0.5. Does it make sense to you guys? How do you guys feel? Is it understandable? Could you relate to what we just did? Of course, I told you already, you have to be sound. That was the reason why I want to give you detail on everything. All right? Because if you have the great detail on everything, you cannot be twisted. It's not possible. So everything we are doing here, very vital. Now, I'm going to ask you another question right now. I'm going to see why you have to pay attention to everything we're talking about. You're going to see the question I'm going to ask you right now. It's something we just talked about some few minutes ago, and only those that were paying attention will be able to really understand it. So let me see who was really paying attention. Guys, look at the question. If A and B are independent, the question is for you to find probability of A given B? That's the question. So if A and B are independent, find the probability of A given B. Anybody with an answer? If A and B are independent, you're not giving any value. You're not giving any value. You're just supposed to find probability of A given B. You're not giving any value. You're just supposed to find this straight up. Guys, why do we have a fewer thumbs up than the viewers? If you're yet to give us a thumb up, please do that as soon as possible. Thank you. So if A and B are independent, find the probability of A given B. All right. Now, if you recollect from the start of this class, I told you that there's a formula when you're talking about A given B, and that's probability of A intersection B over probability of, in this case, B. So of course, if you are told that A and B are independent, one thing they've just told you there is that the intersection probability of A multiplied by probability of B, of course, divided by probability of B. Right? So probability of B, we cancel probability of B. We obviously will be left with probability of A. That's simple. That's simple. So all this thing is all about understanding the concept. That's all. It's just that. That's all. Understand the concept and you're good to go. All right. Probability of A is 0.5. Probability of A is 0.5. Probability of A is 0.5. Probability of B is 0.4. Probability of C is 0.3. If all these events are independent, find the probability that none occur. Find probability that none occur. Find probability that none occur. What's the answer you have? Okay, we have different answers: 0.4, 0.21, 0.94, 0.21, 0.21. All right. Now, all these events are independent. All right. Probability that none of them will occur. It's very simple, guys. What you have to do is, number one, you can go through two different routes. None occur. None occur. That means a way of saying this is probability that neither A nor B nor C occur. And they're all independent. So that means it's like saying probability of neither A, the complement, nor and that means A did not occur and B did not occur and C did not occur. That's a mathematical way of writing this. Neither A nor B nor C. That means A did not occur and B did not all now, and A did not occur and B did not occur and C also did not occur. So none of them did occur. So in this case, to find probability, the complement of this probability that at least two different journeys you can take. Probability that none occur, of course, you can go on to find probability that at least one occur. Now, guys will say, why am I going through probability of at least? I will do for both and you will see. Let's see how it goes. This will obviously be one, because the first, you understand that when you have independent event, their intersection is going to be probability of A complement multiplied by probability of B complement multiplied by probability of C complement. I'm sure you guys agree with this. This is what we have been on for a while. So now the question is, what is probability of A complement? That means, because they said none of them will occur, that means A did not happen, B did not happen, C did not happen. That means the complement happened, and the complement happened, and the complement happened. So of course, this is going to be 1 minus 0.5 multiplied by 1 minus 0.4 multiplied by 1 minus 0.3. All right, that should give me a total of say that's 0.5 right here, that's 0.6 right here, that's 0.7 right here. This is 0.3. This is going to be 0.3 times 0.7. That'll be 0.21. All right. Now, this is probably an easy route. Can we use the other route I talked about? This is quite fast, easy, and simple. I love it. But you can also show your prowess in probability and go through a different route. Now that you know that you are asked to find probabilities that are non-occur, you know already that if an event was non-occur, what's going to be the complement of that event, guys? The complement is obviously going to be at least 1. All right. Now, I can go on to find probability of at least none here. You say, how? Good. Probability of at least none is the same thing as probability of A union B union C. Don't forget, we did that already. All right. So probability of A union B union C is obviously, remember what I taught you guys. This is going to be very long. Guys, I want you to do this. Can you please do this quickly? Can you do this under like 3 seconds? Solve with me, so that in case you have a question like this. What's probability of at least one occurring here? What's going to be the probability of at least one occurring here, guys? Let me probably you solve that question quickly. I would love that too. That's going to open your eyes to how to go about things. Solve for probability of at least one. At least one. This was probability that none occur. Now probability of at least one will be 1 minus 0.21. I get, but can you solve without moving through complement? I understand. You got that obviously from 1 minus 0.21. I don't want you to solve using 1 minus 0.21. Go on to solve with the whole formula. That means I want you to go on to use this formula. Probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. Can you go on and use this quickly? What did you get as this? Of course, using this will be 0.5. Since they're independent, 0.5 plus 0.4 plus 0.3 minus A intersection B. Since they're independent, will be the multiplication of A and B. That will be 0.2. A intersection C, that will be 0.15 minus B intersection C, that will be 0.12. Then plus this times this times this. That will be 5 times 4, 0.2 times 0.6. All right, what do you get while solving this? Do we have an answer there? Just in case. Just in case you come about a question that needed you to move through this route, I just needed to expose this to you. Do you go through the whole work? And are you very sure of this, of all the things I've done? I don't have a calculator here. Anyway, so I don't keep you guys, uh, trying to solve this. I could probably do this probably in a different class so that you understand it better. But the whole point is you could move through at least one to go through the non scenario. All right. Now, okay. Oh, okay. Okay, somebody said this is 0.06. Okay, okay. That's probably where the error is coming from. 0.06. Okay. All right. Thank you for that. So if you go through this, you would see that it's very possible for you to move through this route without having to go through using this concept. This concept is very correct, very good, but just to show your ability to move through a different route, that's why we did this. So if you are done doing this, I'm sure you got the answer of 0.79. All right. So 0.79 was for at least one. So for you to get for none, then you will go on to now say 1 minus. Of course, I'm acting like as if you have not solved this before. Imagine you have not solved this at all and you wanted to go out. After you get 0.79 as at least 1, you can now go on to solve knowing complementary event is 1 minus the event. So that means 1 minus 0.79 will give you for none. That will be 0.21. You can see it's the same answer. So it's just the way you go about things. It's quite very simple and straightforward. So you can see it works either way. So look at this question, the last question on independent events, and we have this one is an oral work. If probability of A is 0, can A be independent of B? If probability of A is 0, can A be independent of B? We don't have to write that. If probability of A is 0, can A be independent of B? If probability of A is 0, can A be independent of B? Any answer? We'll use the last 10 minutes to the last 12 minutes or thereabout. Yes, you are actually correct. If probability of A is 0, A can be independent of B. That's just very correct. So that what will just happen there is that if probability of A is 0, then obviously you know that probability of A times probability of B, which was probability of A intersection B. That means this will obviously be 0 times probability of B, which will obviously be 0. That means probability of A intersection B will be 0, which is actually possible. So A can be independent of B. That's just something you need to know. So guys, we have to spend the next about 10 minutes quickly on something very simple and very straightforward. It's very vital also, and we need to talk about it so that we do not leave it out. So it's called mutually exclusive events. Now, we have successfully covered complementary events. We successfully covered union of events, successfully covered intersection of events. We've successfully covered independent events. Now, we want to talk about mutually exclusive events. Mutually exclusive events. Wherever we stop at, wherever the time is out, we'll stop right there because we have We have just a few more minutes, and don't worry, I'm going to be very timely. Now, look up at this mutually exclusive event. After this, we'll be left with conditional probability. All right, this and conditional probability are the last two we'll be dealing with. So look at this right now. Mutually exclusive event is a very, very exciting, simple, straightforward aspect of mathematics on probability. The meaning of mutually exclusive is just once an event occurs, if I say A and B are mutually exclusive, if A and B are mutually exclusive, that means if A occur, A will prevent B from occurring. That's the meaning of mutually exclusive. Mutually exclusive means the occurrence of one event prevents the occurrence of the other event. That means if two events are mutually exclusive, they cannot happen simultaneously. It's more like they are enemies. And if one is happening, the second one cannot happen. If you just want to do it that way. So mutually exclusive events are very, very, of course, you can understand what will happen, guys. If I tell you, let me just tell you something quickly. If I told you that two events are mutually exclusive, guys, and I say find probability of A union B, can anybody give me what the answer to this will be? With what I just said, if A and B are mutually exclusive events, what's going to be the union probability of A union B? In case you are wondering what it's going to be, remember, generally, without knowing if they are mutually exclusive or not, we always say probability of A plus probability of B minus probability of A intersection B was this, right? But if two events are mutually exclusive, no, you are not correct to saying the answer is an empty set. It's not an empty set, all right? If two events are mutually exclusive, the only thing that will not happen, guys, is that, no, it's not null set. The only thing that won't happen is their intersection. That means the diagram for mutually exclusive events. You can have their union, though. It's not a null set. Look at, this is A, this is B. This is the diagram for a mutually exclusive event. You can see right now, A and B, they are mutual. Once you see a diagram like this, they could write this in an objective question and say, what does this event represent? What's going on here? Of course, if you see something like this, a diagram like this, that's telling the first thing that comes to your mind is that they are mutually exclusive. That means two of them cannot be in the same. You know, this thing we used to draw and we'll set them together. These things happening here meant that what happened, this event happened, event A happened, and event B was happening also. That means they had like a connection there. But since we said mutually exclusive event, the happening of one prevents the happening of the other one. So it's never going to happen. We're never going to have a case where the two events are intersecting. They are mutually exclusive. The occurrence of one prevents the occurrence of the other one. So once you see a question that tells you they are mutually exclusive, just know one thing. Probability of A intersection B is always zero. It's always zero. It will never happen. That means probability of it's an impossible thing for A and B to intersect when they were mutually exclusive. Don't forget, I told you that under probability, when you see something is zero, it means impossible. When it's one, it means certain. So if you are told to find the union of two events that are mutually exclusive, what you have to do is to just say probability of A union B obviously will be probability of A plus probability of B. Simple. If they are mutually exclusive. If they are mutually exclusive, that means the intersection will never happen. All right. I'm sure you are taking very great notes because I'm very interested in your notes. So it's quite a very important aspect of probability. All right. Now, Let's look at a question very quickly. Guys, look at this question. Just take it down. You yourself will understand that you will understand the kind of events going on here. In a single throw of a fair dice, in a single throw of a fair dice, in a single throw of a fair dice, what is the probability that an odd number in a single throw of a fair dice, what is the probability that an odd number or a perfect square greater than 1 shows up? Or a perfect square greater than 1 shows up. In a single throw of a fair dice, what is the probability that an odd number or a perfect square greater than 1, not 2, don't see this as 2, 1, shows up? Can you give me an answer quickly? In a single throw of a fair dice, what's the probability that an odd number or a perfect square greater than 1 shows up? Now, do we have an answer yet? Now, guys, pay attention to this. This is a perfect example of a mutually exclusive event. In case you are wondering what kind of events can you give as an example, look at this situation. Now, you throw a fair dice up. You are asked that what's the probability that an odd number or a perfect square greater than 1 shows up. First of all, can you have, you are asked, you want to find, A was odd number, event B was perfect square greater than 1. Look at these two things. Now, you are asked to find the probability that an odd number or a perfect square greater than 1 shows up. That means you are finding probability that A union B. Now, obviously, imagine you did not understand what was going on here. You would have gone on to say probability of A plus probability of B minus probability of A intersection B. Of course, they did not give you what probability of A was, so you have to go and find out yourself. So when you have a single throw of a fair dice, you will know that the outcomes are 1, 2, 3, 4, 5, 6. Now, probability of an odd number showing up. 1 is an odd number, 3 is an odd number, 5 is an odd number. All right? So the probability of A is what? You know that the event space is 1, 3, 5. Number of elements in that event space is 3 over the number of sample space is 6. That'll be 1 over 2. So the probability of A is 1 over 2. All right? That's settled. What's going to be perfect square greater than 1? Perfect square greater than 1. Now, when you look at your sample space again, you have perfect square greater than 1. Greater than 1, don't forget, not equals to 1. 1 is a perfect square, but greater than 1. Of course, the only perfect square greater than 1 here is 4. So that event has the element as 4. If they did not write perfect square greater than 1, you would have had 1 and 4 inside here. All right? If they did not say perfect square greater than 1, if they said perfect square, it would have been 1, 4. And in that case, you would have had an intersection, because don't forget, odd numbers had 1, 3, and 5. All right? So if they just said perfect square, it would not have been a mutually exclusive event, because you would have had, it's more like saying event A was event A, we had 1, 3, and 5. Now, for event B, we had only 4. All I'm saying here is that if you were dealing with perfect square alone, you would have had 1, 4 here, and that would have been that would not have been a mutually exclusive event. But if you look at this, the possibility of an odd number showing up or this happening, of course, it will be probability of A plus probability of B minus probability of A intersection B. Now, probability of A intersection B, that means probability of A and B happening. That means there's an intersection. In this case, you can see that probability of A intersection B is actually 0. There is no intersection. All right. So if you are asked to just find A intersection B, I'm sure you guys understand this. You would have said it was empty set. All right. Don't forget, we're dealing with probability when we say 0. So don't go and write empty set or something. Now, A intersection B obviously would have been empty set. And if you want to define probability of an empty set, all you have to ask yourself is probability of A intersection B will be what's the number of elements in the empty set? 0 over what's the number of total sample? 6. That would have been 0. That's how we got this. So obviously, probability of A union B here will be equals to what's probability of A? 1 over 2 plus what's probability of B? 1 over 6. What did you guys get as your final answer? 2 over 3. All right, so this is oh, somebody is saying we can count everything once and still get forward. You can use different easy way for a simple question because it was a simple question. Those of you counting and using the manual means, but guys, let me tell you one thing. When you need to understand this way so that when you get to a much more technical work, you can be, it's not every time you'll be able to count like you are probably trying to count. All right. So guys, this is going to be where we're going to stop, obviously, because we have done really great tonight. I really love your participation. It was really great. We had we solved, I don't know, this class and probably 2 classes ago, which one we solved the most. We solved lots of questions in today's class. It was quite very great. I love that. I love you are more exposed to more questions. That will really help you a lot in your coming exams. So guys, prepare for a beautiful test and a very beautiful and wonderful test. Make sure you're well grounded. From everything we have done, we'll be testing ourselves on them. We'll still have one last class for probability, and that will cover more questions on mutually exclusive events and conditional probability. So we still have one more class to end everything up. So whenever that will happen, we'll talk about it. All right. Yeah, this person asking if they both coexist. Yes, if they both coexist, that's what you would have done, what you just wrote. All right. That's what you would have done. But that would not have been a mutually exclusive event. So you'd have just done that normally. But in the case where you have a mutually exclusive event, you cannot have an intersection of those 2 events. So you'll be having of just probability of A plus probability of B, as you can see right here. So guys, thank you very much for joining. You guys are great. Sincerely, you guys are great. I'm rooting for your success so much. I'm really rooting for you guys. And I'm going to be very proud of you. You're going to succeed greatly. And all this will not be in vain. All right. You guys should keep at it. Make sure you have your notes. Make sure you do your best. Burn the midnight oil. Do whatever you have to do to succeed. You can succeed. Thank you guys for joining. We'll be seeing each other very soon. All right. Take care of yourself. Bye-bye.